This video covers text tokenization. I'll discuss some common terminology and challenges in text tokenization, and then I'll show a simple example of how to tokenize text using basic Python commands, regular expressions, and existing NLP libraries. Text tokenization is a critical first step for most natural language processing tasks. Typically, when processing text, you'll start by running a fairly standard NLP pipeline that includes a tokenizer, as well as usually some other tools like part-of-speech taggers, which we'll learn about later this semester. An NLP pipeline generally starts by separating words in running text or tokenizing them. It'll also normalize them. So for example, if there are both British and American English spellings, it can switch everything to one or the other. And then it'll segment the sentences, which can be really useful for defining contextual boundaries. Initially, it might seem straightforward to tokenize text, but there are actually a lot of gray areas. For example, in the sentence here, how many words are there? Do we count or the first main as a word? And there isn't actually a correct answer to those questions. Instead, it depends on what will be most useful for the specific task at hand. An additional complicating factor that can come in when you're counting how many unique words there are is determining what a unique word actually is. So is it a word that has never been seen before in its current word form? So for example, in the example here, cats would be a unique word, or is it a word whose base lemma has never been seen, in which case cats in the example would not be a new word, it'd be a second occurrence of cat. Furthermore, what if we see a second occurrence of the exact same word, like what we see in the example here with the word but? In this case, clearly the second occurrence of the same word isn't a new word, but it is a new token. So in NLP, we typically distinguish between elements of a vocabulary and instantiations of those elements by referring to them as types and tokens, respectively. So in the example here, we have 14 tokens, or 16 if you count the comma and period as individual tokens rather than components of the words preceding them. But only 13 types, or 15 again if you're counting the punctuation separately, since the word but is included in this sentence twice. You'll usually see the number of tokens in a text segment or corpus referred to as N, whereas you'll see the types represented as a vocabulary V. Modern NLP corpora are really large, as you can see from the counts included here. The Google Ngrams corpus, which includes segments of text from the web, contains 13 million types and 1 trillion tokens. So some other issues that can come up with text tokenization are shown here. When tokenizing text, we need to decide whether to ignore punctuation, separate individual constituents of contractions, ignore capitalization, or consider multi-word expressions as a single token. And although the examples so far have only been in English, this is an issue across languages. So for example, we see the same issues with contractions in French, and in some languages the individual tokens aren't separated with spaces, so that can present additional challenges. There's actually a relatively reliable algorithm for segmenting words in Chinese text, where you start a pointer at the beginning of the string, find the longest word in a dictionary that matches the string starting at that pointer, move the pointer forward to the end of that word, and then repeat. However, that algorithm doesn't transfer well to other languages. So this is just one of many things that makes multilingual or cross-lingual natural language processing both really interesting and really challenging. So now that I've covered the terminology and some of the challenges associated with text tokenization, I can go ahead and show some examples of how to do it in Python. So I'll go ahead and work through a couple different ways to do the same thing. First, let's say we don't want to use any pre-built Python libraries. So if we wanted a really simple no-frills text tokenizer, we could just use Python's split function. So we have our title, and I'll go ahead and add a text string. So notice that the string has some contractions, punctuation, and a multi-word expression. So this should be a fun example. So now we'll go ahead and do our basic kind of Python split function tokenization. And we see our tokens here. Now, maybe we actually want to be a little bit fancier than this and use a regular expression so that we don't have an exclamation mark attached to that final token. We can go ahead and do that. So I'll import the regular expression library. So we're saying we want to keep contractions together right now, and we want to consider any sequence of one or more word character. So that's what this \w is. It's basically a shortcut that includes all ASCII characters and digits. So we want to consider any sequence of one or more word character or apostrophe as a single individual token. So we can go ahead and run that. And here's our output. So now the thing about using regular expressions is that although it is 100% possible to build a flexible, accurate tokenizer entirely from scratch using them, the expressions are going to get really complex really quickly. So fortunately for us, other people have done all that hard work already, so we don't necessarily need to reinvent the wheel when we're doing text tokenization. So two really popular Python libraries for NLP are NLTK and Spacy, and I'll show you how to do text tokenization in both of them now. So first we'll use NLTK, and we need to download one of the pre-trained tokenization models from NLTK. And then after that, we can just load the tokenizer directly and run it on our text. Now you can see that this output is a bit different from previously because it splits apart the contractions and it also retains the exclamation mark as a separate token. Both of these behaviors could potentially be useful to a downstream application. So now finally I'll go ahead and do the same example using Spacy. So we'll start off by importing the English model in Spacy, since that's the language we're tokenizing right now, and we will instantiate it. And then we'll create a tokenizer using the default punctuation and structural rules for English, and we'll go ahead and give it our text string. And then we see that the default tokenizer produces the same output as our NLTK tokenizer. Now note that if we'd wanted to, we could have changed the settings for this tokenizer so that they were different from the default. Since we didn't change the settings, we could have also just run the full default English NLP pipeline on our text and gotten the tokens that way. So that's how we can tokenize our own text. Tokenization is a really useful and crucial building block for most NLP applications and is necessary for most of the techniques we'll cover in this course.